Yeah, we never finished this.
Oh, we didn't finish the question. Huh.
What question? No, because then you were like, oh, we're out of time.
Sorry, let's finish that. So, I'm glad you said that, Megan. Sorry. AgCl solid, we're in equilibrium with Ag plus AQ and Cl minus AQ. So this is where we left off with the common ion effect. Did we write a question? Okay. So I said if some NaCl solid is added to this, AgNO3 solid is added to this solution, in what direction will equilibrium shift? Okay. All right. What? What? You got what's going on? What T's? You're gonna give me a heart attack right now.
I am tired.
These are ions. Ag plus, Cl minus, because this is ionic, and when you dissolve it,
sure.
it's okay. I'm glad you. I would rather you make sure than not say anything. So I'm sorry I was a little dramatic in the heart attack comment, but I almost did. So those are ions because this is ionic. It's dissolved in water. If we sprinkle some AgNO3 into this solution, something is going to happen. It's going to shift one way or the other because this here is going to get screwed up. It's balanced now, but when I add AgNO3, because this is saturated means it's at equilibrium. So if it's saturated, it's balanced. But if we add AgNO3, it's going to screw up our balance. Who thinks they know? It's called common ion effect. You with me, Brad? Common ion effect. What's the common ion? Before you answer that, what does the word common mean? The same or something similar.
Everybody has.
Right? So, it's okay. But you're right. What's the common ion in this problem? Reread the question. Let's say this has AgCl solution in it, and I dump some AgNO3 in it. That's the question. It's not very exciting, but that's what this question is asking. What's the common ion? Ag plus, because when you put AgNO3 in water, it does the same thing. It breaks down into Ag plus and NO3 minus. It dissolves. It dissociates. Why? That's very soluble on table F. We already learned all this stuff. So the similarity, the common ion, is right here. So essentially what I'm doing by adding AgNO3 into this solution is I'm adding or increasing the amount of Ag plus. Now you've already learned this. So Ag plus is on this side. If I add more of it, what happens to this? It goes down. So which way does it shift? To the left. So the answer to the question is it shifts to the left, or it shifts towards the reactants. It shifts towards the reactants because you're adding more of the product, causing it to be imbalanced. So it has to shift this way to balance out to going back to equilibrium. All right. So all common ion effect questions, all of them shift to the left. All of them, because the ions are only on the product side. So I only do one quick example. I'm really not that worried about it. I just give you one example in case you see something like that on your quiz on Friday. Maybe you will. All right. So now let's talk about a bigger unit, organic chemistry. All right.
This unit fun.
This is we get to play with these in lab.
Ooh.
So period 7 is going to help me build these things. I picked period 7 because there's a lot more hands in period 7. Plus, you guys are a little bit ahead of period 1. Not period 1's fault. It's because I missed a bunch of days there a while ago. But anyways, so or mornings at least. But we're going to be making these. These are organic structures. The black one in the middle is carbon, and the yellow ones are hydrogen. So we're going to be making a bunch of these. So when I say organic, I want you to think one thing in particular. What is it? Carbon, yes. So, put 3 stars. This is a huge deal. Only substances containing carbon are considered organic. So in real life, when I say real life, I mean like regular people, not chemists, use the word organic, they're probably talking about food or something like that. Okay? So you want to go buy an organic grass-fed burger. Okay, that's what people use that term. But in here, it's totally different. We're talking about chemicals or substances that contain carbon. So technically, anything in the world that has carbon in it is considered organic in chemistry terms. So, is water organic? No, it doesn't have carbon in it. Okay? Is carbon dioxide? Yeah, CO2. It has carbon in it. It's that simple. Okay? I don't really need to give you examples because we're going to be going through a lot of examples. Okay? So only things with carbon are considered organic. I've seen questions on the Regents. Which of the following is an organic substance? They'll have 3 choices that don't have carbon, 1 that does. It's like one of the easiest questions you could get. Okay? It's on frequently, so that's good. So that's the first thing to understand about organic. What's the other thing? Organic compounds are all around us all the time. CO2, for example. Anywhere you've ever been where you smell something that smells like chemicals or fumey or just doesn't smell right, probably an organic compound. Okay? Nail polish remover, organic compound. Gasoline, organic compound. Kerosene, organic compound. Someone think of some other things that smell pretty bad. Alcohol,
Asparagus.
Organic compound. Paint thinner, organic compound. What?
Asparagus.
Asparagus is probably organic, so it has carbon in it, yes. Not probably, it is organic.
7th graders.
Are they organic?
7th graders are probably producing fumes and
Being organic?
other things. They're organic, yes. Humans are organic, yes, because we have carbon.
Is my footprint organic?
Is what?
Is my footprint organic?
Is your footprint organic? If you have any skin cells on the footprint, yes.
Are you picking up what I'm putting down?
Yes.
He's
I got it.
Okay, he's getting it.
Alright, let's talk about some properties, some general properties of organic compounds here. So, general properties. Oh, and before I actually give the list here, you need reference tables.
Other admiral properties?
Yes.
What was it
Yay.
Are there admiral properties? Maybe there's lieutenant as well.
It's going to be a fun unit.
Alright, everyone needs reference tables.
Yay.
You're going to learn about P, Q, and R. Isn't there an expression like mind your P's and Q's?
Yeah.
What does that mean?
Are they talking about
Finds
conclusions
importance.
I
and...
don't know what that means.
Yes, that is what it means.
What does
Yes,
being confused
I like that file.
yes. Okay, now, who doesn't have reference tables? Everyone go to tables P and Q.
Hypotheses and conclusions.
Flower child? No? There they are. Alright, what's table P say?
Organic people.
Organic prefixes, good. What's table Q say? Homologous series of hydrocarbons, right. Go to table R.
Yay.
Organic functional group.
Organic functional groups. We're going to deal with R down the road a little bit. Right now we're going to focus on P and Q.
He's on down.
So I'm just making you aware, so write this somewhere around your thing here. Tables P, Q, and R. Those are going to be really important, so just don't forget that they are there, okay? P, Q, and R. So now let's talk about the properties. So, organic substances do not contain metals. Therefore, it's carbon with other nonmetals. What type of bonding does it have? Covalent. Good job. So, organics have covalent bonding. Covalent bonding. And most of the time, so I'm going to write usually, non-polar covalent. Non-polar covalent. So, organic molecules like this one here, this is a structure of methane gas. Methane gas, which is also called natural gas, is a non-polar covalent bond, or molecule. So covalent, we think organic, we think covalent, and specifically nonpolar. Now, what did we learn about nonpolars this year? Well, think back to the tin can lid lab. We put it on the ring stand, lit the candle underneath it. What happened? Few things, 3 of them melted, the rest didn't melt. Does anyone remember one of the things that melted? Wax. Guess what whack is? Wax.
That's wacky, yo.
Why did I say that?
What?
Guess.
Today is a good day.
Guess what wax is?
Carbon.
It's an organic molecule. It's organic. Guess what's in it?
Carbon.
Carbon. And it melted.
Would have guessed.
And it melted with a candle. What am I getting at? It's weak. Yes, very good.
Yay.
They have weak forces of attraction. Weak forces of attraction. Yes, very good. Non-polar substances have weak forces of attraction. In parentheses, I want you to put van der Waals / dispersion. We learned about those a while ago. I'll move in a second. So we got dispersion or van der Waals. Dispersion is the type of van der Waals. But, yeah, in general, organics are very volatile. They evaporate easily. If you go pump some gas, everybody can smell it because it's evaporating. Nail polish remover, everybody can smell it because it's evaporating. Volatile means it evaporates easy. Weak forces, yeah.
What about steel?
Steel, yeah, now you're throwing some curveballs at me. But I can hit that one because steel isn't a chemical compound. So it's different. It's a mixture, a physical mixture of carbon with iron. So technically, since they're not bonding, it doesn't apply to this. It's kind of confusing, but that's why it's not considered organic. But good question. So weak force of attraction, van der Waals, and dispersion. What else did we learn this year about weak forces of attraction? Substances that have weak forces do this very quickly.
Melt. Burn.
Melt. Good. Give me another word.
React.
Keep going. You melt it, and then you can do what to it?
Evaporate.
How do you do it?
Boil.
Violently. Boil. Right. So substances that have weak forces, like organic compounds, have low or high melting points. Low. Low melting points. Low melting points and low boiling points. This is all relative, of course. What does that mean? If I'm comparing organic molecule A and organic molecule B, one of them is going to be stronger. One of them is going to have a higher melting point or lower. But in general, that's why I wrote general, organics compared to other things in the world, like ionic, for example, are very weak, low melting, low boiling. Okay? The salt on the tin can lid will never melt. Okay? Candle can't do it. But the wax will, because the wax is organic. Okay? So those are some very important points. I'm forgetting something right now. What else was I going to say there? I'm losing it here. If they have only non-metals, do they conduct electricity? No, because there's no ions. So organics do not conduct electricity. They do not conduct electricity. They are called non-electrolytes. What's an electrolyte? Don't say it's in Gatorade. So I've taught you, I remember a lot of you on your journal said, I don't know what electrolyte is. So I went over it again and again. Someone please remember, I hope I shall know. Yes, good. A salt is an electrolyte. I'll let you off the hook. But what is an electrolyte?
A salt.
I need the definition of it. Do you remember?
It conducts electricity in salt.
Yeah,
In water.
in water, right. So when you put, that brings me to the next thing. When you put organics in water,
If it's not a salt, is it pepper?
good one. Actually, that's funny because pepper doesn't dissolve in water,
Yay.
and neither does this. So organics do not dissolve in water. How do you know that? How do you know that already from something I wrote down?
Because they're not electrolytes.
You remember the video with the guys, AC/DC? Remember the 2 polar bears and then the 2 brown bears?
I can do it.
They were like polar and polar, not polar and non-polar, whatever. Right. So non-polar doesn't mix with polar water because they're opposite. Remember, like dissolves like. So these do not dissolve in water. So I'm kind of hitting you with everything at once here as far as the general properties, and then we're going to get into details of how to draw, name, and identify these things. All right, that's what your reference tables are for. So we'll do as much as we can today. We got this unit takes a little bit of time, but this is all the main ideas here. There's another one that I don't want to talk about yet. I'm going to wait till we start drawing some structures out, but it has to do with boiling point. So we'll talk about that, but not yet. All right, I think we're good. Just for review, non-polar, symmetrical or asymmetrical? Hold on, Tara knows. Non-polar, symmetrical or asymmetrical? I can't hear you. One more time? I don't know. One more time? Good job! Symmetrical, I heard you that time. Symmetrical, yeah, non-polar, symmetrical. You guys got to remember that. That's a good review. Alright, so here we go. Let's talk about table Q and P at the same time. We're going to learn about these things. Hydrocarbons. Hydrocarbons. Amik, what's a hydrocarbon? I feel like you know.
It's got carbon and hydrogen.
Good job.
Yay.
It's a molecule, an organic molecule, that only contains C's and H's. My marker's dying. Let me use it a little bit more. Molecule that only contains C's and H's, carbons and hydrogens. Look at table Q. There are 3 types of hydrocarbons. Brad, what are they? Yep, 3 types. Look at the left side of table Q.
Oh.
All the way left.
Alkanes.
Alkanes, good.
Alkenes and alkynes.
Alkenes and alkynes. Good job. You said them all right. Good. So in your notes, write alkanes. You don't need a space. Alkene. Alkenes. And alkynes. Those are the 3 types of hydrocarbons. And the analogy I used in period 2 today, which I thought was pretty good, just kind of popped up in my brain, so I'm going to throw it out there to you guys. To help you understand what these are, there are 3 different types of organic molecules, but the title of Q is homologous series. What does homologous mean? The same or similar, right? So here's what it means. All alkanes are similar to each other in one way, and then similar to these 2 in another way. So all alkenes are similar to each other in one way, and similar to the other 2 in a different way. The analogy I used was like breeds of dogs. Okay, so just stay with me. Alkanes are like golden retrievers. Alkenes are like bulldogs. Alkynes, German shepherd. So all 3 are dogs. That's what they have in common. But golden retrievers are more in common with other golden retrievers than they do with bulldogs or shepherds. And then the same is said for the other 2. It's a decent analogy if you follow me. So these are a group of compounds. There's like thousands of them. Thousands of them that are very similar because they're all alkanes. But they also have similarities to these 2 as well. That's why they're in one chart, but they're separated by 3 different names. So hopefully that made some sense. Now, look at table Q and tell me, what is the big difference between the 3? Don't say it, just think. You're looking at table Q, and you're looking at the big difference between the 3 hydrocarbons, alkene, alkene, and alkyne. I would look at the example. That's where we're focused here. Go ahead, Eden.
I was going to say the bonds, they have a single, double, and a triple.
There it is. Perfect. Alkenes have just single bonds. That's all alkenes have, single bonds. And I'm going to focus on just the carbon-carbon bonds because carbon-hydrogen is always a single bond. Hydrogen can't make a double bond. It only has 1 electron. So it can only make a single. So we're looking at the CC in the middle there, those 2 carbons in the middle. So, well, it's the only 2 carbons, I guess, on that chart. The alkene has a double bond. The alkene has a double, and the alkyne has a triple bond. So that's how they are different from each other, but how they're similar is they all have carbons and hydrogens. Okay? So just for fun here, which one do you think has the strongest bonds? Maybe the highest boiling point or something like that.
Alkynes.
Why?
Because triple bond is a stronger bond.
Triple bond's harder to break. Even though when we melt or boil, we don't break bonds. That doesn't happen. But I want you to think triple bond is stronger than single. The only way to break bonds is a chemical reaction. When you melt, boil, that you're just breaking forces. We've talked about that. But the concept still applies. So this one would be strongest, that's weakest. Yes?
So should we rate like the more bonds, the stronger?
Yeah, more bonds, stronger it is. Yep, sure. Yes?
Doesn't it have to do with the triple bonds being shorter than the single
Yep,
bonds?
the triple bonds are short. So the real reason behind it, like the college explanation, is you have two nuclei which are attracted to the other one's electrons. So you have a positive nucleus. So you have this carbon and this carbon. The positive nucleus is attracted to this one's electrons. This electron is attracted to this nucleus. So if your triple bond is shorter, these two can get closer to each other, and that's good. That makes it stronger. But there reaches a certain point when they get too close, the nucleus repels and the whole thing explodes. So that can happen too. Anyways, back to this. All right, so now what we're going to do, we got a little time. We're going to focus on alkanes. That's the first thing we're going to learn about is alkanes. So alkanes are all single bonds. Alkanes are single bond. They're also called saturated hydrocarbons. Saturated hydrocarbons. They're also called saturated. And what that means is it means it's, we'll put in I'm using the same word. I know you're not supposed to. It's saturated with hydrogens. So because alkanes have single bonds, the carbons are holding the maximum number of hydrogens that it can hold, which is 4. If it's just one carbon, it can hold 4. Almost every other carbon can either hold 3 or 2, depending on the structure. I'm probably confusing you. We're going to get into all this. But saturated means it's saturated. It's kind of like a sponge is saturated with water. It would be dripping with water. It can't hold any more water. These are saturated with hydrogens. They can't hold any more hydrogen. They have the max amount. So alkanes are called saturated because they're single bonded. And I always make the connection with classes single saturated. Saturated single. The two S's. Try and keep those together. Saturated is single bonded. So we'll talk more about that. But here's what I want to try and do before the bell. Let's get a couple examples. If I write CH4 and I write C3H8, let's see if we can name these. Let's see if we can name those structures. So here's how we do it. And if I get cut off, we'll pick it up tomorrow. Don't forget, this worksheet right here, due tomorrow, okay? That worksheet's due tomorrow. Go to table P. Tell me, what's the prefix for one carbon? This has one carbon in it. Meth. So we write meth. Now do me a favor. Go to the general formula for alkane. General formula. Plug 1 in for N. How many H's will that provide or produce? If 1 is in for N. Okay.
Wait, if 1 is for N?
Yeah, if you put 1 in for N on the general formula for alkanes. Do you have table Q open? Oh, well then that's the issue. Go to table Q and plug 1 in for N on the general formula for alkane. How many H's will you get? 4. Isn't it 2N plus 2?
Yes.
So 2 times 1 is 2. 2 plus 2 is 4. So what does that mean? Stay with me. Just real quick. This is an alkane because this formula fits on that chart next to alkane. In other words, CH4 wouldn't fit for an alkene or an alkyne if you plug 1 in for N. It wouldn't work. CH4 only fits for an alkane. So, how does that help you? That means the ending ends in A-N-E. It's an alkane, so we call it methane. That's where the name comes from. So if I give you the formula, you see how many carbons you have, write the prefix, then plug that number in for N and see where it fits. Does it fit an alkane, an alkene, or an alkyne? So this one is obviously an alkane as well. Anyone want to quick give me the name if they think they know? What is it? Propane, because 3 is prop on table Q, or table P. ANE, because it's alkane, it fits the general formula CnH2n plus 2. That adds up to 8. If you plug 3 in for N, adds up to 8. So I went kind of quick. We'll do more tomorrow. I'll stop there. Just that worksheet. Just that worksheet for homework tonight.